In this lesson, you'll learn every essential skill needed to read and analyze table data with confidence. We'll walk through how to interpret rows and columns, compare values accurately, calculate changes and rates, and recognize important patterns that appear in SAT questions. By the end, you'll know exactly how to break down any table the test gives you. A table is one of the most common data formats on the SAT math section. It organizes information into rows and columns so you can compare numbers quickly and clearly. But even though tables look simple, SAT questions often test much more than basic reading. Many problems require you to identify patterns, such as how a value increases, decreases, or stays constant as another value changes. Other questions ask you to compare categories, calculate totals or averages, or determine the missing value in a sequence. Sometimes you'll need to combine information from different rows, or notice how two variables relate to each other. A key challenge is that SAT questions frequently hide traps in the numbers. A value that looks large may not actually represent the biggest change. Two rows may appear similar but follow different rules. Or a pattern may seem consistent until the final entry breaks the rule. The most important skill is to read the table carefully and focus on how the numbers behave, not just what they look like. Once you understand the relationship behind the data, you can solve any table question with confidence. Here is our first example, a simple input-output table. Tables like this appear frequently on the SAT, and your goal is to determine how each input value is mapped to its corresponding output. At first glance, the numbers may look random, but SAT questions almost always follow a consistent pattern or rule. Start by examining how the table is organized. The left column shows the input values, and the right column shows the outputs. Your first step is to look at how the outputs change as the inputs increase. Ask yourself, does the output increase by a constant amount each time? Does it stay the same? Does it change in a predictable way? If the difference between outputs is constant, the rule is likely linear. If the changes grow or shrink in a non-constant way, the rule may be nonlinear. In this example, we will analyze how the outputs change and identify the exact relationship that maps each input to each output. Understanding how to read these tables is the foundation for all later SAT questions involving patterns, equations, and modeling. Once you learn to recognize the rule quickly, these problems become some of the easiest points on the test. Here is the answer. The equation that fits this table is y equals 3x plus 1. Let's walk through why this rule works. As x increases by 1, the value of y increases by 3 each time. This constant rate of change is the key feature of a linear pattern. If the increase were inconsistent, the table would be nonlinear. But here, the pattern is steady and predictable. Now let's verify the equation with each row. When x is 1, plugging into the rule gives y equals 3 times 1 plus 1 equals 4. When x is 2, y equals 3 times 2 plus 1 equals 7. For x equals 3, the rule gives y equals 10. And when x is 4, the output is 13. All rows follow the exact same rule, which confirms that y equals 3x plus 1 describes the relationship perfectly. A quick reminder. For any table, the equation must work for every row, not just one or two. Consistency is everything in SAT math data analysis. Whenever you work with an input-output table, the key is to look for how the numbers change from one row to the next. Don't focus only on the visual layout of the table, focus on the pattern. Ask yourself 3 questions. First, what happens when the input increases? Second, does the output increase by a constant amount? And third, is there a clear rule that connects the two? If the change in the output is always the same, the relationship is linear. If the change grows or shrinks, the relationship may be nonlinear. By checking the pattern row by row, you can quickly identify the rule behind any table and avoid common mistakes on the SAT. Here is a new table for pattern recognition. Take a look at how the values of y change as x increases. Start by comparing each row. From x equals 1 to x equals 2, y goes from 5 to 9. From x equals 2 to x equals 3, y increases from 9 to 13. And from x equals 3 to x equals 4, y goes from 13 to 17. Notice that y increases by the same amount each time x increases by 1. This constant rate of change tells us that the relationship is linear. Your task is to identify the rule that connects x to y. Think about how much y grows each step, and what value y would have when x equals 0. We'll confirm the exact equation on the next page. Let's confirm the rule that connects x and y in this table. As x increases by 1 each time, y increases by 4. Because this change is constant, we know the relationship is linear, and the slope is 4. Now think about what happens when x equals 0. If x equals 1 gives y equals 5, then moving one step back means y would be 1. This value becomes the constant term in the equation. Putting the slope and the constant together, we get the rule. Y equals 4x plus 1. Check each row, and you'll see that this equation matches every pair in the table. Here are the 4 key skills you need for recognizing patterns in a table. First, look for consistent change. When the increase in y is always the same as x increases, you are likely dealing with a linear pattern. Second, compare the rows step by step. The difference between consecutive values almost always reveals the rule. Third, estimate what happens when x equals 0. You can do this by stepping backward from any known pair, which helps you find the intercept. Finally, confirm your equation with all the rows. A correct rule should work for every pair in the table. With these 4 skills, you can identify patterns quickly and accurately on the SAT. Now let's practice identifying whether a table shows a linear or nonlinear relationship. Look at the values in this table. As x increases from 1 to 4, pay close attention to how y changes each time. When x goes from 1 to 2, y increases from 5 to 9, that's an increase of 4. When x goes from 2 to 3, y increases from 9 to 15, this time the increase is 6. And when x goes from 3 to 4, y increases from 15 to 23, now the increase is 8. Notice what's happening. The change in y keeps getting larger each step. It's not staying constant. If the change in y were the same every time, the pattern would be linear. But here, the differences are growing, 4, then 6, then 8, which means this pattern is nonlinear. Always remember, linear patterns grow at a constant rate. Nonlinear patterns grow at an increasing or decreasing rate. Take a moment and see if you can clearly recognize how the pattern behaves in this table. Now let's analyze this table and explain why the pattern is nonlinear. Start by looking at how the output value, y, changes as x increases. When x increases from 1 to 2, y goes from 5 to 9, which is an increase of 4. From 2 to 3, y goes from 9 to 15, an increase of 6. And from 3 to 4, y goes from 15 to 23, an increase of 8. These differences, 4, then 6, then 8, are not the same. Because the change in y is growing each time, the pattern does not follow a straight line relationship. A linear pattern must have a constant rate of change, and this table does not. Instead, this type of increasing difference suggests a nonlinear relationship, often quadratic or another curved pattern. Here's the key idea. If the change in y is different at every step, the rule cannot be linear. Always check the differences. They will reveal the pattern immediately. Here are the fastest ways to check whether a table represents a linear rule. First, look at how the output, y, changes as x increases. If the change in y is the same every time, like plus 3, plus 3, plus 3, then the pattern is linear. A constant step increase is the signature of a straight line relationship. Next, once you know the slope, use any single xy pair to find the intercept. This gives you the complete equation, such as y equals 3x plus 1. Finally, always verify your rule with every row. A rule is only correct if it works for all pairs in the table. Here's the quick test. If the differences in y are constant, the rule is linear. If the differences keep growing or shrinking, the pattern is nonlinear. Use these checks, and you can identify linear rules instantly. In this example, one value in the table is missing. Your job is to determine which number should fill the empty space. First, examine how the y values change as x increases. From 1 to 2, y goes from 4 to 7, an increase of 3. Check the next available pair. From x equals 2 to x equals 4, y increases from 7 to 13, which is 2 steps of plus 3 each. This suggests that the pattern increases by 3 every time x increases by 1. Using this pattern, we can fill in the missing value when x equals 3. 7 plus 3 gives 10, so the missing entry is 10. Always confirm that your completed table follows a consistent pattern throughout all rows. Let's check the answer for the missing value in the table. We start by looking at how the output changes as x increases. From x equals 1 to x equals 2, the value of y increases from 4 to 7. That's an increase of 3. Next, look at the jump from x equals 2 to x equals 4. The y value goes from 7 to 13, a total increase of 6. Because that represents 2 steps in x, 6 divided by 2 gives 3 per step. This confirms that the pattern increases by 3 each time x increases by 1. Using this idea, we can fill in the missing value when x equals 3. Starting from 7, add 3 and we get 10. So the missing entry is 10. Finally, verify that all rows follow the same rule: 4, 7, 10, 13. The differences are consistently 3, which confirms that the table follows a linear pattern. And that is why the correct missing value is 10. Here are the most common traps students fall into when completing missing value tables on the SAT. First, many students rely on the visual impression and assume a pattern is linear simply because the values appear to increase steadily. But what matters is not the direction of change, but whether the amount of change is constant. Second, some decide the rule too early, using only the first 2 rows of the table. Always check every row before forming a conclusion. Third, a table where the differences do not match cannot be linear, even if the numbers look close. A single mismatch means the pattern follows a different rule. Fourth, students sometimes think that growing differences automatically mean an exponential pattern. But exponential patterns require a constant ratio, not a constant difference. And finally, one of the biggest traps is misunderstanding negative patterns. Just because the output decreases does not make the rule nonlinear. If the change is consistent, for example, -3 every time, the pattern is still linear. By understanding these traps, you can complete any missing value table with confidence and avoid the most common mistakes seen on the SAT. Now let's practice a classic SAT-style table question where you must choose the equation that fits the data. Look at the table and focus on how y changes as x increases. From 1 to 2, y goes from 7 to 10, an increase of 3. From 2 to 3, it goes from 10 to 13, again plus 3. And from 3 to 4, it increases from 13 to 16, another plus 3. Because the change in y is consistently 3 each time, the relationship must be linear. A linear rule has the form y equals mx plus b, where m is the constant rate of change. Since y increases by 3 each time, the slope m is 3. Now check where the line begins. If x equals 1 gives y equals 7, then the intercept must be 4, because 3 times 1 plus 4 equals 7. So the equation that matches every row of the table is y equals 3x plus 4. On SAT equation selection questions, always identify the rate of change first, then use any row to find the intercept. This prevents guessing and guarantees the correct choice every time. Let's review why the correct equation for this table is y equals 3x plus 4. Start by checking how y changes as x increases. Each step adds exactly 3. 7 to 10 is plus 3, 10 to 13 is plus 3, and 13 to 16 is plus 3. Because the rate of change is constant, the pattern is linear with a slope of 3. Next, find the intercept by using any row in the table. If x equals 1 gives y equals 7, then substituting into the linear form y equals mx plus b gives 7 equals 3 times 1 plus b, so b must be 4. Now confirm the equation matches every row. If x equals 2, 3 times 2 plus 4 equals 10. If x equals 3, 3 times 3 plus 4 equals 13. If x equals 4, 3 times 4 plus 4 equals 16. Every value fits. The other answer choices fail. 2x plus 5 doesn't match after the first row, 4x plus 2 grows too quickly, and x squared plus 6 works only for the first 2 points before breaking. Because y equals 3x plus 4 is the only equation that matches the entire table, it is the correct SAT-style answer. Here are the fastest and most reliable rules for testing equations in SAT table problems. First, always check the rate of change. If the differences between the y values are not constant, the equation cannot be linear. This step alone eliminates many wrong choices quickly. Second, plug in the easiest row, usually the one where x is 0 or 1. If the equation fails even that simple test, eliminate it immediately. Third, after one correct match, test just one more row. If the equation matches 2 rows, it almost always fits the entire table. If it breaks even once, discard it without hesitation. Fourth, ignore how the table looks. SAT questions often create patterns that appear linear or nonlinear, but the visual impression is misleading. The numeric differences are what matter. Finally, watch for reversed patterns. A decreasing table can still be perfectly linear as long as the differences are constant. By applying these quick checks, you can evaluate equations in seconds and choose the correct SAT answer with confidence and speed. Here is your intermediate practice problem. This time, the table includes negative values and decimals, just like what you may see on the SAT. Your task is to determine the missing value in the final row. Look carefully at how X is changing from row to row, and think about how the corresponding Y values should change. Even when the numbers are negative, or include decimals, or move irregularly, the same principle applies. Identify the pattern in X, compare it to the pattern in Y, and use that relationship to fill in the missing value. Take your time, analyze the pattern carefully, and try to predict what the final Y value should be. You have 60 seconds. Pause the video now and give it your best attempt. Now let's walk through the solution to this intermediate missing value problem. First, look at how the X values change. From negative 2.5 to negative 1.0, from negative 1 to 0.5, and from 0.5 to 2.0, each step increases by exactly 1.5. Even though these numbers include negatives and decimals, the step size stays consistent. Next, examine how the Y values change. 4 to 7 is plus 3, and 7 to 10 is also plus 3. This tells us that the relationship is linear, with a constant change of 3 in Y for every 1.5 increase in X. Since the pattern is consistent, we can extend it to find the missing value. The last known Y value is 10.0. Add the same change, which is plus 3, and you get 13.0. Therefore, the missing value in the table is 13. This method, checking the change in X, then the change in Y, works even when the numbers look complicated. It's one of the most reliable strategies for SAT table questions. Here's an advanced table problem. The values of X and Y do not follow a simple linear pattern, so your task is to identify which equation best fits the relationship. Look closely at how Y changes as X increases, and decide whether the pattern is linear or nonlinear. Then choose the equation that matches the trend shown in the table. Pause the video and take 60 seconds to think. Let's walk through the answer step by step. We're given a table where the X values increase in small increments, but the Y values rise faster and faster. This already hints that the relationship is nonlinear. Start with step 1. Plug each X value into the candidate equation B, which is Y equals 2X squared minus 3. If you try X equals 1.5, you get 1.5. For X equals 2, the output is 5. For X equals 2.5, the equation gives 9.5. And for X equals 3, the equation produces 15. These values follow the same upward trend shown in the table. Now step 2. Check the pattern of growth. Notice how the Y values increase slowly at first, then much more rapidly. That accelerating pattern is the signature of a quadratic function. Choice B is the only option that matches both the computed values and the overall growth behavior. The other equations either grow too slowly or remain linear, so they can't match the curvature seen in the table. Therefore, the correct equation is B, y equals 2x squared minus 3. Great job making it to the end of this lesson. You've learned the core skills that SAT Math uses again and again: how to read tables, how to map inputs to outputs, how to recognize linear and nonlinear patterns, how to fill in missing values accurately, and how to match a table to the correct equation. These aren't just techniques for a test. They're habits of logical thinking that help you move faster and more confidently through any data-driven problem. From here, your next steps are simple. Keep practicing with new tables, check patterns carefully before committing to an answer, and build up your ability to spot structure at a glance. Accuracy comes first, and speed naturally follows as these patterns become familiar. You're now prepared to take on more advanced SAT Math challenges. Keep going. You're becoming a stronger and smarter test taker every day.